Ask you for attention for the second part of Heiko's talk. So we are again looking forward to see some amazing movies and pictures, or not, or more equations this time. So go ahead, please. Thank you.
Thank you, Martin. Thank you very much. So this will be a slightly different talk, like not the opposite, but less videos, sorry. And there will be at least one equation, so let's see if you can spot it. And so I thought I wave to the guys out there, like, can you see us? We start now. Before it was this overview, right? So I showed you like a colorful basket of everything. And now the idea is that we dive a bit deeper into one particular thing. And as you could already tell from the program, this is going to be collective decision making. And I'm presenting here this talk in two parts. The first part will be, I'm counting on you, so I hope you can help me a little bit. We will try to define a little model for collective decision making. Not so much because the model is so great and so super easy applicable to everything, but to give you a better chance or to enable you to get a better intuition of what is collective decision making really and what's relevant in a very general way in that concept. And then the second part, I forgot it for a moment, but this is going to be another particularity of collective decision making. There's something called the speed versus accuracy trade-off, which is, if you ask me, an insanely interesting thing, which is almost like a natural law, if you ask me. And we will try to understand that and look into that a little bit, as much as the time allows. All right, so just a little motivation. So the pictures here are random, so don't try to see a connection. So I think collective decision making is really essential in a way that it's almost present in any swarm scenario. So collective decision making for me is not just one scenario of swarm robotics, it's actually an enabling technology that you will use very often, or you can use it as a model and you will then see it all the time in all these different swarm scenarios. So also another way how I try to usually pitch it, and I've gotten some negative feedback on that, but I still haven't understood what these people mean. So maybe you can tell me. I'm saying, well, we build our robot swarms from autonomous individual robots, right? So each unit is autonomous, which means basically it can make its own decisions, it's energy autonomous and so on. And then collective decision making, I'm saying, is some kind of requirement to implement this macro scale, so the global autonomy. So for your swarm to be autonomous as a whole, it has to make decisions by itself, right? And that will necessarily be collective decisions because the swarm is not really something real, it's consisting, or it's the sum of all its parts or even more. And then you can also spot or interpret different tasks or scenarios as collective decision making, like task allocation I've mentioned before is actually some form of collective decision making, only then you don't want to have a consensus. So let's say you have two tasks, A and B, then task allocation means, depending on some cost function, that maybe I want to have 80% on A, 20% on B, and you can actually do that with almost the same technology as collective decision making. And then also synchronization is some kind of collective decision making. So you try to, you don't meet at a spot, but you meet at a certain periodic time, and that's also agreeing on something. This is a consensus on a certain moment in time, arguably. So when you think about collective decision making, and I believe you have already some rough intuition about it, then we have all these different challenges, and I'm not saying this is a complete list. Well, first of all, this is multi-robot systems. So we have distributed robots, and it's not always so easy to coordinate. So this is just a general problem in multi-robotics, I guess. And then there's these time and accuracy constraints. So time just means, okay, I want to converge on an answer within a given time boundary. And accuracy here means maybe these options come with different qualities. So actually there's like a correct and an incorrect or suboptimal solution, and accuracy would mean, like high accuracy means I actually converge on the optimal option. So 100% of the swarm says option A, which actually turns out to be the best one, is what they agree on. So usually, as I said, if it's like, if you ask me, if it's a true swarm, then you have only local communication, which is actually a problem, right? So we as a human society, we do collective decision making. It's only that usually we well, do it by global communication, because the authorities tell you, like in Germany, it's always on Sundays, we're going to have this election, then you can inform yourself, and well, then it's you going there, and it's, okay, one local place where you drop then your vote, but in the end, it's, you know, summed up and calculated globally in the whole system. So, but here in the swarm, it's only one guy asking, talking to its neighbors, and they might even misunderstand when are they supposed to start to have a collective decision. So that's actually what I have here as the last point. So that's even already a challenge. Or how does an individual in the swarm understand that now actually it's asked to be part in a collective decision-making process, and when to stop? That's something that I tried to answer before, according to the question. So also, like when does or how can the swarm agree on, now we have a consensus and now we stop the process, and we have actually a collective decision. And then this, what I mean by coupling of opinion and embodiment, this is what you see here in this movie on the left. So this is an example of, well, just one-dimensional but collective motion, or you can argue this is some form of one-dimensional flocking. And there, the opinion is actually a physical feature. So the direction of motion is your opinion. I'm going clockwise, I'm going counterclockwise. And so the motion obviously is influenced by that, and that also determines who will be your neighbor in the next time step. So you have this somehow tricky combination that your opinion also determines your motion, and then it's making things complicated and challenging. And before we get into this first part, so this is still like just some stuff I want to show you before. This is something I will not really go into many details, but to make you aware that just knowing about the options you can choose from, that might already be a problem. So you can assume different scenarios, right? You could say, well, what we usually do in our modeling approaches, we keep everything as simple as possible. So it's a binary decision-making problem. You have option A, option B, and all the robots know there are two options, and maybe they even know the qualities of these options. But you can imagine any other case, right? You have 3 options, you have 100 options, you have infinite number of options. Maybe they are even continuous and not discrete. And then how do you make sure that they actually learn about these options? How do they explore them? And here you see some examples. So this is again from my own work. On the left, you see this video I've shown you before of these ePugs driving around, and they have this ground sensor so they can detect the color of these tiles. And their task is to agree on, are there more black tiles or more white tiles? And we call this collective perception. I'm, again, not sure if that's really a good way of expressing it, because in theory, one robot could do that, right? You could have one robot that like somehow drives around, and over some while, it will learn about the true ratio of black to white. Here, of course, we parallelize it with many robots, and then they also well, somehow talk to each other. They share, I'm for this opinion, so there's a color code. I'm not sure what it is, but blue for black and red for white. And then they try to find a consensus. So here you could still like do it with one robot, right? Just exploring the whole environment. That's not so difficult. But then what we try to do here on this, this right-hand side, this is more recent work that we're going to present at IROS this year, I think, where we have a dynamic environment. So it's the same idea, same task more or less. You have these tiles, only now we project them with a video projector from the ceiling, and this time it's actually kilobots. And they agree on, okay, the black tiles are in majority, but then over some time it actually changes, and then they have to reconsider their collective decision, right? So it's a dynamic environment, you have to stay adaptive, you have to monitor the environment, and then depending on how fast the environment is changing, maybe one robot can't do it anymore, because until it learns that, yeah, now actually it changed, maybe it changed again, right? So then it's a true multi-robot setting. And dissemination of information, that's not really something visualized here, but if you explore a new option or if you learn about a new a quality of an option, then maybe you have to disseminate that. So you talk to your neighbors, you tell them, hey, option B is really great, it has that and that quality, so you have to implement, by local information usually, this like gossiping and diffusion of information throughout the swarm. All right, but that's not something I will dive into. Instead, let's try to come up with a model. I know it sounds a bit boring, like why would we want to do a model? Actually, you want to work on robots, right? But I think it's really good to understand, actually, for me, it's about an intuition, to gain an intuition about fundamentals of collective decision making. And so first, actually, again, I hate definitions, but sometimes they help. So there's this quite nice paper from Gabriele Valentini and colleagues that they published 2 years ago in Frontiers in Robotics and AI, called the best of n problem in robot swarms. So they define this best of n problem. I don't really like the letter n here because usually I use the capital N for the number of robots. So now there's another n, but okay. So you have lower n options to choose from, and this would be the simple case that actually you know them before, right? So somehow all the robots learned about all options. And then what is a decision? What is the collective decision? Well, you want to have some large majority, right? So in the extreme case, you would ask for a consensus. But you can maybe also be a bit like less greedy. So you say M robots are enough if it's like considerably more than half of the swarm, right? So depends also a bit on how many options you have. If you have like 1,000 options, then asking for more than half of the swarm is maybe already asking for a lot. If it's just 2 options, then maybe you would like to have something like 90%, 95% in favor of one of the options. And if they have qualities, then maybe even for the better quality. And they also have this taxonomy, so some nice schematic drawings in that paper. I'm not going into the details here, but so best of n can have, for example, like symmetric option qualities. So then it becomes, like if you think about a system problem with just 2 options, and they have either the same quality or just there's no quality defined. So it's just about finding a consensus, and you only care about the symmetry breaking, right? So both options are fine, but you have to agree on something, right? So that's a special case, and then the asymmetric case would be the more intuitive one maybe, where you have qualities, different qualities for each option. So there is the best option to choose from. And you might even have costs of these options, so then it's getting a bit more complex, but I don't want to go into this. And yeah, so if you have qualities, then you can actually talk about accuracy, because it's not just about agreeing on something, but agreeing on the right thing. But for now, we just say we have the symmetric case, so we just ask the swarm to agree on something. So please form a majority, and we don't care, is it option A, B, or something else. Okay, So now I'm pushing towards a model, and you have to be a bit patient because my motivation for the model is somehow like from the back. So at first we do the model, and then later hopefully you understand why we do this. So I'm asking for your trust that I built up in the talk before, let's say. Okay, so we want to do some stochastic modeling, and one thing that is often assumed in simple models of these collective systems is a well mixture. What does it mean? Well, so for example, each robot has a certain internal state, especially its opinion, right? So it can be in favor of blue, in favor of red. That would be its state. And well mixed now means that independently of the position of the robot, so you randomly pick one robot, then it should always be the same probability to find either red or blue. So there's no spatial correlation in the system whatsoever, which is most of the time not true, okay? So this is a very rough simplification, but it makes the models much, much more, well, easier, makes them easier and also, well, simpler basically. So let's, although it's wrong, let's assume we can do that for now. And then once you talk about well-mixed systems, I mean, here we have the photo. Hopefully you're not playing lotteries, right? So there's, don't know from whom this quote, like lotteries are a tax on not knowing math, right? So even though it's tempting, you shouldn't do it, unless it's for a good cause, who knows. So I'm not sure how it works in other countries, but in Germany, there's this like state lottery, and when they show, I think by now they don't show it on TV anymore, but they show the drawing, then there's even like an official there, like a notary or something, checking the well mixture basically, right? Is there no bias, is everything fine? So even by law, this well mixture is, well, asked for. And then the idea is, well, here all marbles are blue, yellow, all the same color, that's what I mean. So the idea would be that we have different colors to represent the different robot states. And here, because it's collective decision making, it will be the opinion of the robot, like, hey, I like yellow better, I like blue better. Okay. And we start with so we're going through a procedure iteratively. We will go through 3 different models. 2 are suboptimal or incorrect, and the last one will be the one that's actually doing what we want. So don't be too much disturbed by the first model. But we try to start from literature, let's say. So if you think about these lottery models, so somehow we represent these robots by drawing marbles. This is actually a well-established concept in math and also in physics. You have these Ehrenfest models. And there's one famous one by the Ehrenfest couple. So this is Paul and Tatjana Ehrenfest. And they were physicists and invented this Ehrenfest Ehrenfest model, which was introduced in 1907, so quite some time ago, for modeling basically, or trying to understand the second law of thermodynamics that you should all know. And here it's mostly about diffusion. And I just read this little text to you. So we have an urn with n marbles, so capital N, that's the number of robots, right? 2 colors, blue and yellow, that's the 2 opinions. And maybe we start from all blue, which sounds funny because that would be the consensus already. Now we start drawing. Whenever we draw a blue marble, we replace it with yellow, and if we draw a yellow marble, we replace it with blue. That's just their definition. And it's also called the dog flea model. Any idea why? Dog flea. So it's like, this is the impression. So you have these little animals living on your dog. Like, I'm not sure. I'm not a dog owner, but I'm told that exists. So any idea what that could be? So you have two dogs, right? So different owners that live at different houses. One has green fleas, the other one purple ones, and then they meet. Right? Well, they go for a walk, they meet, they play together, and in the end, both have half of the population of the other one, right? So that's the dog flea model to remember. Okay, so this is just a schematic drawing. So we do a draw without replacement. In step 2, you notice the color. Okay, let's say it's yellow. Then that means you put the yellow marble in your pocket. It doesn't go back, but instead you pull out a blue marble out of your pocket and put it back into the urn, right? So this is what we said, how this is defined. And now the question for you, so again, if all marbles are blue in the beginning, and then we do this kind of drawing, and not just once, we iterate over it, like we do that like 100 times or so, what would you expect? What happens? Right, so the answer is it should end up like half-half, right? So that's not, well, not too surprising probably. Okay, so this is the idea. We start, so 1 here means 100% blue. So this is what I call the swarm fraction. So without limiting generality, we just say we count blue marbles. So 100% blue means 1. And then the gray lines here are like the different samples, because it's a stochastic process that realize here. So if you repeat it, you will get different outcomes. But in average, you will actually see this like kind of exponential decrease and end up on this equilibrium. And this is just one other way of representing that. So whenever you have a deviation from the 50-50 state, so this marble rolls a little bit left or right, then due to gravity, it will be pushed back to the inside. And I told you, so in the talk before, I mentioned these two feedbacks, negative feedback, positive feedback, and you were supposed to remember that. So what kind of feedback is that? You have a 50-50 chance. Yeah, so this is negative, right? So like the centrifugal governor, when there's a deviation, you're pushed back. So there are forces that push you back onto the equilibrium. Is that a good model for collective decision making? No, of course not, right? So this is like the opposite of collective decision making. We start from a consensus and then we go to a 50-50 state, which is like the undecided state, unless we would do some task allocation, and that would actually be what we want. But here it's like the undecided state, 50-50, that's not what we want. So we have to fix this. Do you have an idea how we can fix the Ehrenfest Earn model to have a better representation of a collective decision-making problem? So these are the rules. Which ones would you change? Yeah, so how do you change the color? So if I draw a yellow one, what do you do? You don't change your opinion. Like, you're speaking as a marble or as you? Yeah. Well, that would somehow work a bit, but then we never really change something, right? So it's true. So if I draw yellow, I should not add more blue. So I should somehow add more yellow, right? And now it's just a technical problem of how to implement that. I mean, with modern Earn technology, we can do that. So this is actually a model that was already published. So this is from at least a book by Manfred Eigen and Rotild Winkler, Laws of the Game, where they really present side by side the Ehrenfest Earn model and this one, which is kind of the opposite. So now it's about positive feedback, right? So we start here from 50-50, otherwise it would be boring. And whenever we draw a blue marble, we replace it by a yellow one from the, we replace a yellow one from the urn with a blue marble. So we draw with replacement and then like fish for another one from the urn and replace that. So here with this schema, it will be much clearer. So whenever I draw a yellow one, I do that with replacement. So I draw it, I look at it, yellow, I put it back into the urn, and then I search for a blue one, remove that, put it in my pocket, pull out of my pocket a yellow one, and put that in, right? So what happened by drawing a yellow marble, the number of yellow marbles in the urn increased, right? And that maybe makes some sense. So, like long story short, this is what you would get. So we start from 50-50, and now you see that, well, I didn't put an average expected evolution here, right? Because that would be just like the 50-50 line. But you see from the gray realizations of individual samples that you get this divergence, so you start from 50-50. What determines whether you go towards 1 or towards 0? Just shout at me. Yeah, first draw or some of the early draws, right? It's fluctuation. That was actually part of the definition of self-organization. So by a random event, I mean, in the beginning you have a 50-50 chance for blue and yellow. So by a random event you get some bias, and once you have one more of one kind, then the probability is higher to get more of that. It doesn't mean it has to win, right? Sometimes you can see that it goes down and then back again. This is just fluctuations because you have a, well, you could also argue this is finite size effects, right? And then here you have, in this representation, well, we put the system on an edge, and then again you have this fluctuation, because what determines whether it goes left or right, right? So, I mean, the mathematician would say it will stay there forever, but actually it's like you add some energy, so there's some variance in the system, and then it will roll down either way. And maybe we can already start thinking about where's the connection to collective decision making. So these drawings here, so what does it mean for a collective decision making swarm? If we say here drawing a yellow marble means we find a blue one that we replace by a yellow one. What is our interpretation for collective decision making? What do the robots do to achieve that? Any idea? Right, so it must be some interaction between at least two robots talking to each other or something. So there's like one robot, in this case a yellow robot, finding or running into a blue robot and trying to convince it to convert, right? Or maybe something that is hidden somehow is that there's maybe even a group of robots, like 2 or 3 of these yellow guys, finding a blue guy and then convincing that to switch to yellow, right? So this is about the interaction system or model or process that actually makes that happen. And if you think about it, so again here we have a higher probability to convince a blue one of getting yellow if you have a lot of yellow in the urn, right? Okay, another question, is this actually a good model of collective decision making? The answer is no, but I would be interested in why. It depends actually, yeah? So I'm not sure if I got it. So you say it's deterministic? Or?
So just because a yellow robot says change to yellow doesn't mean that that's actually the best idea. So
right.
If you say every time you come across a yellow, then you would change your mind to yellow. That's not going to necessarily give you the collective decision that you want, and a chance that maybe you will change your mind based on.
Okay, yeah, so the idea was, well, just because this yellow guy tries to convince you, maybe it's not really a better option or it's not a good thing to switch. I mean, that's something that's connected to whether it actually has a quality to be blue or yellow. There's no, we say here that we have the symmetric case, so there's not really, like blue or yellow is not really better than one or the other. So what defines whether a switch is good or bad is actually whether it helps to increase the maturity, right? So that makes some sense. So I give you another chance to argue, yeah? The tipping point is too narrow. So that you speak about the around 0.5? Mm-hmm. So how would you change that? Mm-hmm. So I'm not sure if I understood. Can you rephrase? Okay. So it's okay. Yeah. So if you look into the dynamics around 0.5 here, that was somehow represented by the tip over there, and then what he means, I think, is to make it a bit wider, and so you have more time to decide whether you go left or right. Okay. Yeah, that's actually interesting. Again, still not really the point I wanted to make. So maybe I should have shown you some of these trajectories from a natural swarm. So there's actually experiments, for example, about collective motion in locusts. So this is these little ugly animals, insects, walking around, and they put them into a ring, and then it's like the video I showed you before, like they can go clockwise or counterclockwise, and you can actually count how many are going clockwise, how many are going counterclockwise. So you can, what we produced here with our simple model, you can actually measure in a natural system. And what you would see there is that they never, or almost never, converge on a full consensus. So I'm not sure how much time we still have, but last chance to think about, like, why is 100% consensus in an at least natural system maybe not the best idea? Yeah? You have no exploration. Exactly. So if you, I mean, like from a mathematical point of view, these two extremes, 0 and 1, are absorbing. Once you're there, you will never go get away. Because what you have to think about is, if everything is blue, and I draw a blue one, of course, then I'm asked to look for a yellow one. So that's actually like an infinite loop in your program, if you like. So you will not find something, so you end up there. I mean, that's like putting it shortly. So I have to like accelerate a bit. So we will change this, and so this is the model we converge on. It looks a bit more complicated. Also, being reminded that I'm leaving out half of it here. So what we add, so we use still the, well, it's still a bit like the Eigen model, but we introduce another step where we ask for explicit, like, do we want to have positive feedback in this round or not? So do we want to have positive or negative feedback in this round? And then we implement that. So drawing yellow, throwing the dice, saying this time it's positive feedback, then we replace a blue one with a yellow one. And what we get is then something like this, and this looks more natural. So if you look into the locusts, for example, this is what you would see there. So you get a large majority of one thing, but not everybody converges on that. So you have exploration. What does that mean? That means you still have some agents that look for the other option, because it might be a dynamic system, right? So the other option might actually get more interesting over time. And then in this schema here, you see that now the little ball would not roll all the way, but it would actually receive a force from the boundaries to stay a bit away. So I have to be a bit faster, because what I didn't tell you yet is how we actually determine whether you want to have positive feedback in that particular drawing round or not. And for that, we can just define a function. And going back to the other models, you can, so this model here is actually generic, and it incorporates the two other models. Because you could say with the Ehrenfest model, we just never ever have positive feedback. With the Eigen model, we just always have positive feedback. And this is here represented as a function over the system state S, which is the swarm fraction, how many are currently blue, right? And it's a constant, so it would just never change. And for this like swarm urn model, you would have a function, this is arbitrary, more or less, but so I just take here the sine function, and what you implement is that in this middle region around the 50-50 state, you have a high probability for positive feedback, and at the boundaries around 0 and 1, you have, like most of the time, you have negative feedback, and then you actually get these trajectories. Okay, and if I would be allowed to give you homework, then I would ask you to calculate this little equation there, because this is already the complete model. So what you would need to do there is thinking of all 4 cases. Drawing from the majority, having positive feedback or negative feedback, drawing from the minority and having positive or negative feedback. And then you actually can calculate with very simple probability theory this function. And this would give you the expected change of like how much the number of blue marbles in the system changes. Unfortunately, we don't really have the time to look into that now, but if you're interested, I can point you to places where you can read about this, actually in the book, or there's also a paper on that. Let me know if you need help to find it. So I want to spend some time also on the second part, which is the speed versus accuracy trade-off. And well, the original plan was that I would talk a little bit about this scenario here, how we implement that on the robots. Given that the time is running, I will do that just very quickly. So again, these are the kilobots. We have 100 of these kilobots. They are initially in the 50-50 setting, so 50 are blue, 50 are red, and then we have 2 sides, the red side on the right-hand side and the blue side on the left-hand side, and they now actually come with qualities, and the quality of the red option is double as good as the blue one. How do they learn about it? They have to go there. So there's some navigation going on. Well, you can tell roughly from the shadows of the robots. So there's a light beacon, and so they know if I want to check out the blue side, do I have to do phototaxis or anti-phototaxis? So I have to approach the light or run away from the light. There they will receive a message about the quality of that site, and then they will go back into this inner part, like the nest area, and disseminate this information. So they will send messages like, hey, blue is great, switch to blue. The other robots, the passive robots, just receive these messages, and then they count. Okay, I received 5 messages, 3 were blue, 2 were red, so I switched to blue, or if I was already blue, I stay blue, right? And this way it wouldn't work, so you have to add one more thing. So those that have a higher quality, so those that explored red, they disseminate it proportionally more according to the increased quality. So if double quality means basically they disseminate it for 2 times longer than the blue guys, and this is how you generate positive feedback. Okay, I skipped something. So now about the speed versus accuracy. And again, I think this is really a very intriguing, interesting thing, because it's not only true for swarms. Actually, people first published about it for human decision making. So if you take part in a psychological experiment, what they would do is they give you some actually quite simple task, like, don't know, that you hear 3 beeps, and after the 3rd beep you have to push a button, or you get some cards that have different symbols, and they come in 2 stacks. Like, let's say the 2 symbols are circles and pluses, or crosses, and then you can draw 1 card from each stack as you like, and there's 1 stack where the ratio between circles and crosses is 50-50, and with the other one is 2-to-1. And they ask you to like quickly decide which one is which one. So they put you under pressure, right? And only then you can actually really measure the speed versus accuracy trade-off. So you can either be fast or accurate, right? So if you're quick, the accuracy will be low. If you're accurate, you will take time, right? And this is something you have experienced yourself, certainly at some time as well. You shouldn't, like, it doesn't mean that for your career decisions, you just have to wait an infinite time to make an infinitely accurate decision, right? So this doesn't work like that. Some more diagrams. So this is a schematic one. This is accuracy. This is error rate. And here you see everything. Well, there are no times, but here you have reaction times up to 700 milliseconds. So it seems like it's just this reaction time thing, right? Like a sprinter at the Olympic Games or so. But it's actually much more than that. So don't be tricked that it's just like your human reaction time. It's a bit more than that. But for that, we have to go into some details. And for this video here, I told you this decision rule for an individual. I told you that they count incoming messages, right? 5 messages. If more are blue, then I switch to blue. So we call this the decision rule, or the individual decision mechanism. And what I just told you is the majority rule, right? So you collect opinions, and then you go with the majority. So this is my interpretation of that. So majority rule is basically our democracy, right? So maybe Trump is not the best example, but because he didn't have a majority, but okay, let's not get into that. And then, of course, also Brexit is an interesting outcome of like a majority decision, right? So this is just to remember. So I, as a robot, I ask my neighbors, and then I go with the majority, which is maybe not the best behavior for yourself, because you should inform yourself and then make a maybe more accurate decision instead of just asking your friends. There's another option of how you could implement this, and this would be the voter model. And this is maybe even a bit more weird, because here you pick a random neighbor, and without paying attention to any of your other neighbors, you just switch to the opinion of that particular neighbor. Yeah, that's even worse. Yeah, why would you, like, on the election day, you walk to the door of your neighbor, ring the bell, ask, what are you going to vote for? Ah, okay, then I will do that. Yeah? So you shouldn't do that. But you can actually implement that on these robots, and it seems really silly, right? It's this copycat idea. You just copy the opinion of one randomly selected neighbor. And why do I show you that, right? So shouldn't it be clear that the majority rule is always better, because it's like, at least it takes into account more opinions, right? But I wouldn't have shown this to you if this would be complete garbage. So what we want to look into quickly is, so if we have a swarm, a collective decision-making swarm operating on the majority rule, and we have another one operating on the voter model, how do they perform in terms of the speed versus accuracy trade-off? Is anyone willing to make a guess? Perfect, yeah. So this is actually the true answer. So the voter model is more accurate, but slower, right? And the majority rule is fast, but less accurate. Maybe later we have a little bit of time to try to get an intuitive understanding of that. But yeah, it's not so easy to accept, I think. So the voter model actually gives you higher accuracy. And here I want to show you some results. So these are not really measurements. So this is from a paper I published together with Gabriele Valentini, Eliseo Ferrante, and Marco Dorigo 3 years ago, where we have some models for our 100 kilobots that make these decisions. So this is actually based on a ODE system. So I hide the model from you here. So please go to that paper if you want to know more. And now I just try to explain to you this diagram. So what you see here is basically all different system states that you can achieve. So we actually have 100 robots, right? It's even the title of the paper. And they have to decide between 2 options. And these options come sometimes with a different quality. So you can say that option A has always quality 1, that's constant, but we change the quality of option B. So this is what you see here in the lower curve, that their option B is 0.5, then 0.7, 0.9, up to 0.99. And I've written here that the lower one is easy, the top one is hard. So if the difference between the two opinions is just 0.01, then of course it's really tough for the swarm to decide what is actually really the better option. And why do we have the little Trump there? Well, it is because faster is the majority rule, and Trump here is the mascot for majority rule decisions. How ironic is that? And then, so what we do actually is TVM over TMR. This is the convergence, the time to convergence of the voter model system over the time to convergence of the majority rule. So basically it gives you the factor of how much slower the voter model is compared to the majority rule. And this is for the different initializations. So I can initialize the system 50-50, that would maybe be fair, right? But I can also initialize it close to like almost 100 robots are already in favor of option A. And then you see that you get these funny shapes. So you actually get a very, well, you can't say you get a fast decision for 50-50 because 50-50 is actually a hard initialization for some of the qualities, but the difference then between the two, majority rule and voter model, is not so much anymore. But sometimes, so to make this short, we see that the voter model is like up to something like 20 times slower sometimes than the majority rule. And so there's nothing's for free, right? So if you're fast, that should mean that you're inaccurate. So we can also check that. So this is the same model. Again, the initializations, the different qualities, and now it's this is an exit probability. It's just the probability of reaching the optimum, and we subtract the probability of reaching the optimum of the voter model. No, we subtract the probability of the majority rule from that of the voter model. So if you have a 1 there, that means the voter model is much more accurate than the majority rule, and that would be what is expected. So don't ask me what's happening there for 0.99. That's actually a bit weird, but all the other parts are clear. The voter model is actually more accurate. Okay, and then so almost done. I'm not asking for much more than that, but because I kind of claim that this speed versus accuracy thing is kind of like a natural law to me, at least. So whenever you try to trick it, to play some trick and to get rid of it, like to get more accurate and faster at the same time, there will be some godlike agent somewhere that makes sure you fail. So one thing that might be tempting would be the following. So what about mixing the voter model and the majority rule, right? So we have a swarm of 100 robots. Well, I could just have 50 robots following the majority rule and 50 robots following the voter model, and then maybe I get the best of both worlds, right? So I have robots that decide quickly, and I have robots that decide accurately, and somehow maybe, you know, it combines, and then I have a fast and accurate system. Well, you know the answer, so it won't work, but to have a look, so this is what we're going to do. So instead of having like a homogeneous swarm, all of them following the majority rule, and also not just all following the voter model, we have a mixture of both. And you can also choose, like I want to have 10% majority rule, 90% voter model, or any mixture you want to choose from, right? So you're allowed to be crazy and try anything. Okay, so this will be my last diagram for today that we need to interpret. I hope it's clear enough. Somehow the resolution is not perfect. Excuse me. And so what you see here is, well, it's a two-dimensional optimization problem, right? So it's one dimension here horizontally is the speed, And actually, so don't look too close at the numbers. So if you go to the right-hand side, it means you're faster. And the vertical axis is accuracy, and that means the farther you move up towards the top of the slide, then you get more accurate. And now you see these different symbols. The color code here, I mean, you can barely see the colors, but the color code is for different task difficulties. So the purple up there is for a big difference in quality. So 0.8 quality for one option and 0.2 quality for the other one. So it's easy, relatively easy to distinguish them. And then we get the two qualities closer and closer, and until here, once we have the star symbol, then they are actually of the same quality, so then it's actually hard to define any accuracy. And what you see is, again, this trade-off. So not so much for the purple stuff, they're up in the right-hand top corner, but once you go to these bit more difficult tasks, you see these like almost some lines, right? Like this line and this line. So I have to tell you one more thing. The different sizes of the symbols code the mixture. And here for the diamonds, I've marked that for you. So this little diamond means this is a pure majority rule swarm, and the big one up there is the pure voter model swarm, and in between you have like different mixtures. And you see, like, what does it mean that they live on this line? Well, it means the pure majority rule swarm is obviously fast, but not so accurate. And if you go towards the pure voter model system, then you're getting slower and slower and slower, but at the same time you get more and more accurate, right? So I told you, there's no way of tricking this law. So you can now, as a swarm engineer, you can choose where you want to live on this line, like how accurate and how fast do you want to be, but it's not like all your choice. You have to move along this line. And that's all you can do, right? You can't, well, I would argue you can't really do better, but what I can't do is proving that this is actually always the case. So you're young, eager minds. This is a hard problem. So let me know if you have an idea how to prove that it actually has to be like that. I don't have any idea. Okay, so this is the end. Just some food for thought, or this is the conclusion or take-home lesson. So please try to remember from this that you can think of these earn models, right? So this is an easy way to gain some intuitive understanding of these basically stochastic processes that we call collective decision making. I think it's an essential like building block or something, so it will, like in virtually any swarm system, you will have some form of collective decision making, I believe. Even flocking, for example, you will somehow find that. And then the speed versus accuracy trade-off is something maybe you should keep in your mind that it exists, and there's no easy way out, so I believe you can't trick it. Because for me it's almost like a natural law, but feel free to prove me wrong. And that's really interesting because you see it in individual human beings when you push them, and you see it in ants, and you see it in swarm robots. And well, that's awesome if you ask me. So this is it. I showed you some work from these two guys, Gabriele Valentini, Mohammad Difbansorati. These are the first authors, and there were also some other authors, so please also look into these papers. And again, yeah, so if you're interested, so I have two copies of the book. Feel free to have a look, and thank you very much for your attention. Questions?
Yes, thank you. First question. Let's use Mike again.
I wanted to ask when you were talking about the initialization. So it also matters where you initialize. Like if you put like 50 blue and 50 red, also it matters like your initial neighbors, right? Like if you put all the red in one side and all of the blue on one side, right? So did you like put that into consideration or?
Yeah, the question is about the initialization. So I just mentioned these probabilities like 50-50, 60-40, something. And the question is, shouldn't I also think about who's neighbor of who? So this was, I guess, about this horizontal axis. And yes, sure, the neighbors matter. But this is something I mentioned very early that we just, well, I mentioned it in the first part and I didn't mention it again in the second part. So this is again always well mixed as an assumption because we model it with population models like these ODE systems here where we don't really represent space. So that means we assume a well mixture. But a bit more curious it is once you think about this system, the real robots. And I told you that the well mixture is just a simplification for the modeling. If you look into this, I mean, I could play that for a while and you could try to pay a lot of attention on individual robots. You would see, of course, that there is a spatial correlation. So, I mean, that's actually what we implement, right? So you ask your neighbors, and if the majority of your neighbors is for blue, then you will become blue. So that implements explicitly a spatial correlation, right? So the assumption of a well mixture is wrong, but still good enough to model this system quite precisely. And actually what we do with the robots is we try to enforce a well mixture by doing the following. So you can choose basically the frequency, how often you reconsider, right? So this is the relation between how much distance does a robot cover until it checks its neighbors again, and reconsiders its opinion. And you can actually control that in your algorithm. So this is a way to somehow try to enforce the well mixture. And it will actually help. It will like speed up your system and make it less prone to deadlocks. Yeah.
Another question? Really, no more questions? So you are only looking forward to go to the brewery?
Yeah, you can also talk to me tonight. Just make sure you ask me before I have my third beer.
Maybe it will be even better after.
Yeah, then it's a random answer.
So I have the same nasty question I had for Antonio. So of course everything looks great, but where can you imagine that it will be like the first deployment of this technology in the real world, in real applications? What will be the application which will be influenced the most by this?
Yeah, that's a tough one.
Probably no drones, right?
No, meanwhile, I'm convinced drones are great. I really believe that whenever you implement a robot swarm, you will at some time need to implement some form of collective decision making. So my very like non-creative quick answer would be you will always need it somehow. If I would need to be more specific, like if you think about like precision farming, so I have 10 robots that have to move along a field, then it's like some task allocation problem, and maybe you want to make sure if one breaks down, then the other ones take also these parts that this guy couldn't solve. And then you would have, well, it's a task allocation problem, but you can implement that with methods of collective decision making. And I just forgot my other idea I had. Yeah, well, synchronization would actually also be a form of collective decision making, right? So you have to agree on a time window that's basically a collective decision, and you might need that even on drones, I guess, if you have some communication protocols.
What about autonomous cars? I know that I think Amanda was it who told us that
she has
her,
these model
her
cars.
guess is that it will be autonomous cars, and I think it could be really the truth. So maybe you can have also some decisions there, which way to use to avoid traffic jams. I don't know.
Yeah, so we have some research just started on platooning. So this is autonomous cars lining up very closely, like really strangely closely to each other on the highway. And then, well, I'm not sure, like, is it really collective decision making, but you want to form like different platoons with different properties. Like, where are you going? I mean, on the highway, everybody should go the same direction, but you want to exit at a certain place. Also, maybe a preferred speed. And then it's also, like, for the individual, the question, do I join this platoon over there, but then I have to go fast alone for a while to reach it? Or do I drop back and join the other guys, but they actually go a bit slower than I want? And the idea of, like, when to form a new platoon could be some form of collective decision making, maybe. Yeah.
So do you expect that swarms of RL vehicles will be sooner than swarms of underwater vehicles? So who will be the winner? Because I think RL, like swarms of RL vehicles will be here very soon in army, right? I think they have something already.
Yeah.
But for like public usage, let's say.
Yeah, I mean, what do you gain from me making a prediction just because I throw the dice? No, but what I really like about the underwater swarm robotics is, like from an academic point of view, if you want to do like 3D motion, then I would always try to prefer the underwater setting, because then you can just have you can almost have passive robots based on buoyancy floating around, or on the surface you can have autonomous sailing robots, right? And with the drones, you would always have these battery problems. And we don't want to do battery research, right? So the downside of the underwater swarm, of course, is that you have localization challenges, you have communication challenges, but maybe they are more interesting to work on than developing the next better battery.
Thanks. Yes, we have some comment on this our small panel discussion here.
Yeah, thank you very much for your talk. I was curious, and I'm sorry if you already answered this, but have you looked into what happens when each robot has an initial guess of what the environment looks like, and then bases all their information off of that? Or
so I mean, there's like some initial bias for one of the options or something? Yeah. Well, so I mean, you could say that's almost already what we're doing, because we initialize them to one of the two opinions. There's other works where you actually have an undecided state. So everybody would be uncommitted in the beginning, and then would need to be convinced about switching to one of the options, and then you can still switch to the other one, but only via this uncommitted state. So this is actually inspired by bee behavior, honeybees. So one interpretation of your question could be, that maybe everybody has some specific information about one particular option or something like that, because you have been there before or so. Then of course it would be interesting, and then it's more about like this gossiping and diffusing this information throughout the swarm, right? I mean, another thing to make this more interesting is also, here we already have some exploration, but a few things we are looking into currently is, what if you have many options and all of them are unknown in the beginning? Maybe you have like almost infinitely many options. Then exploration is a much more challenging problem. So it's not just like switch to one random opinion, go there and check it out. but actually it is like, for how long do you want to explore? When should you stop exploring? You know, then everything gets a bit more interesting. Maybe that's somehow resonating with your question.
Yeah, I was just meaning in terms, I think with the way you initialized it, it's stochastic, like it's just randomly initialized, but I meant like, it's not randomly initialized, there's some educated guess at the beginning of how each one is initialized.
Yeah, so this is of course also another interesting aspect that I mean, here we have these really, really naive agents. So here in this example, they don't even compare qualities, right? So everything is just by this modulation of positive feedback. It's just the time for how long you disseminate. Nobody has to compare qualities explicitly. And this is, of course, one extreme. Like, you can argue, why would you do that, right? What you're saying is something like, okay, you can, like here we do everything collectively, right? The individual does almost nothing. What about putting some of that decision-making part into the individual so that an individual can make an educated guess, some more information processing, and then maybe the whole swarm also profits from that. So it's like this continuum, how much of the process do I want to put into the individual, and how much do I outsource into the whole swarm to solve collectively?
We have another question there.
So the banquet will start 15 minutes later?
Is there some research into doing decisions that are like continuous, that they actually can decide that there is 51% black?
So with the tiling, so what do you mean? So whether this is continuous?
So they decide that it's either black or white, right? But couldn't an agent also think that like it's 51% black and 49% white, and then they decide
okay, yeah,
on the real...
Yeah, that's also a good point. Is it this one? So true. So what our agents do here, and this is somehow like similar to the question we just had. So what actually each robot does is they somehow they measure 2 times. For how long did I see a white ground, and for how long did I see a black ground? And then that determines their opinion. So they actually do this comparison, like, okay, like the time for how long I saw these bright tiles was longer, so I'm opinion that white is in the majority. You could, of course, and then they just communicate white seems in majority, right? That's what they communicate. You could, of course, communicate more, so you actually communicate these 2 times that you measured, and they would be like this percentage. So 68% of the time I saw white tiles. What about you, right? And then you could average over these well, continuous measurements, if you like. It would actually be interesting to see whether it changes something. It sounds like you could bring in some more precision somehow, but I'm not perfectly sure. Maybe it might also slow it down.
I guess it's faster.
Yeah, I would like to see. I would try.
Another question? Really feel free to ask more. We have time. Don't worry about the beer and food. But if there is no question, I thank again.
Thank you.
Yes. Thank you for coming to Prague, for accepting our invitation. I have a small present for you.
Thank you
Hope
very
will
much.
Enjoy it. And
Thank you.
Yes, thank you, and enjoy the rest of the stay here.
Thank you very much. Thank you.
I have a few information for you. The first one is regarding the banquet. So after the last